Welcome to IT.Solution, your total network, system, firewall, and security partner.
Welcome to the Explainer. So today we're focusing squarely on ITN Module 12, IPv6 Addressing. And look, if you've been working in networking for a bit, you already know that looking at an IPv6 address for the very first time, well, it can honestly feel like you're trying to read an alien language. But today, we're going to break down the actual mechanics of IPv6 addressing. We'll take it from this daunting string of random-looking numbers and turn it into what it really is, a totally logical, highly automated, and honestly incredibly elegant system. By the end of this, you're going to see exactly how your network devices use this protocol to just communicate seamlessly.
Here is our roadmap for today. We'll be hitting 5 main sections: why we need IPv6, deciphering IPv6 formatting, Unicast, Multicast, and Anycast, global and link local addresses, and finally, dynamic addressing and SLAAC. Let's get right into it.
Section 1, Why we need IPv6.
4.3 billion. Think about that number for a second. That is the absolute theoretical maximum number of IPv4 addresses. Now, back in the day, that sounded infinite, right? But then came the massive explosion of IoT, the Internet of Things, devices. Literally everything connects to the internet now, and we completely outgrew that limit. Sure, we use short-term fixes, like NAT, network address translation, to sort of hide multiple private addresses behind a single public one, but let's be real, those were only ever just band-aids. The time has absolutely come for true, native, end-to-end communication without those translation bottlenecks, and that is exactly the problem IPv6 was engineered from the ground up to solve.
Section 2, Deciphering IPv6 Formatting.
Okay, so the biggest difference here is just pure scale. Unlike the traditional 32-bit IPv4 address that we are all super used to seeing, IPv6 utilizes this massive 128-bit format. To put that into perspective for you, that is roughly 340 undecillion addresses, which means there are literally enough addresses for every single grain of sand on Earth to have multiple IP addresses assigned to it. It's crazy. You simply don't have to worry about conserving public IP space ever again. But obviously writing out 128 ones and zeros by hand, yeah, that would be an absolute nightmare for any network engineer.
So to make it actually readable for us humans, IPv6 is written using 32 hexadecimal digits separated by colons. And the underlying math here is actually quite elegant. Every single hex digit perfectly represents 4 binary bits. So by grouping them into blocks of 4 hex digits, which you'll sometimes hear called a hextet or a quartet, we get exactly 16 binary bits per block. This means when you look at an IPv6 address, your brain doesn't need to panic. You're really just looking at 8 totally manageable chunks of hexadecimal data that the computer seamlessly translates back into that giant 128-bit binary string.
Section 3, Unicast, Multicast, and Anycast.
Now that we know how to read that hex format without our eyes totally glazing over, let's categorize the 3 broad types of IPv6 addresses you're actually going to encounter out in the wild: Unicast, Multicast, and Anycast. Notice what's missing there? Broadcast. Yeah, IPv6 notably does not use traditional broadcast addresses anymore. Instead, it relies on highly specialized multicast addresses, like the all-nodes multicast address, to achieve the exact same result, but way more efficiently, because it doesn't interrupt devices that just don't care about the traffic. Oh, and Anycast is incredibly cool too. It allows multiple routers to share the exact same address, so a packet is just delivered to the nearest available service. Brilliant, right?
But for our purposes today, we're really going to focus heavily on the Unicast address. This is the absolute bread and butter of network communication. It's the primary way a single end-user device, or even a specific router interface, gets identified on the network. But here's a fun twist. Unlike IPv4, where a host usually just gets that one single IP address, IPv6 devices typically juggle a couple of different Unicast addresses all at the same time.
Section 4, Global and Link Local Addresses.
Let's keep zooming in here and dissect the 2 essential Unicast addresses a device is going to have configured. First up is the Global Unicast Address, or GUA. Just think of this one like your standard public IPv4 address. It's globally unique and routable across the entire public IPv6 internet. But right alongside that, the device absolutely must have a link local address, or LLA. This LLA, which by the way always starts in the F80 range, is strictly confined to a single local link or subnet. It is totally non-routable. It's really just there so devices and routers sitting on the exact same local network segment can chat with each other without ever needing to step out onto the wider internet.
Now check this out. What's really interesting is how that 128-bit global Unicast address is just cleanly sliced right down the middle. It's standard practice. You've got a 64-bit prefix on the left side, which handles the network portion. That's the part assigned by your ISP or your local network admin. And then you have a 64-bit interface ID on the right side acting as the host portion. And keeping that interface ID at exactly 64 bits, it's not just a suggestion, it's strongly recommended. Because, as we're going to see in just a minute, all those automated configuration systems absolutely rely on that perfect 64-64 split.
Oh, and tucked right inside that 64-bit prefix is a dedicated subnet ID block. Because it's embedded right there, an organization can just easily increment a single hexadecimal value, like going from 0000 to 0001, then 0002, and so on, to carve out up to 65,536 internal subnets. That means you don't have to do all that complicated, headache-inducing binary subnetting math we were forced to do back in IPv4. You literally just change one single hex digit, and boom, you have a massive, brand-new subnet ready to go. Talk about a game changer.
Section 5. Dynamic Addressing and SLAAC. Finally, let's zoom all the way down to the actual device level to see how a single PC automatically configures its own 128-bit address on the network. See, in IPv4, we heavily rely on DHCP servers to hand out addresses, right? But in IPv6, we have this brilliant stateless method called SLAAC, that's Stateless Address Auto-Configuration. It basically plays out like a simple conversation. Step 1. The PC boots up and sends out an ICMP-v6 router solicitation message, basically yelling, "Hey, is there a router here?" Step 2. The local router replies with a router advertisement. And step 3, the PC uses the info in that advertisement to generate its very own unique host ID. No DHCP server required whatsoever.
So, diving into that automated conversation a bit more. When the router sends that ICMP-v6 router advertisement down to the client, it crucially includes the /64 network prefix. The client device just absorbs that prefix, and instantly it's got the first half of its 128-bit address entirely figured out. Easy, right? But to actually start communicating, it still needs to construct the second half, that 64-bit interface ID we talked about earlier. To build that interface ID, the PC basically has two options. It can either just generate a completely random 64-bit number, which, by the way, newer operating systems tend to prefer for privacy reasons, or it can use the super clever process called EUI64. With EUI64, the PC takes its own physical 48-bit MAC address, literally splits it right down the middle, injects the hex values FFFE into that gap to pad it out to 64 bits, and then flips the 7th bit. Whichever method it goes with, it just takes that 64-bit ID, slaps it onto the router's 64-bit prefix, and boom, its global address is completely built.
But hold on a second, what if another device on the network somehow generated the exact same interface ID? To prevent total network chaos, the PC performs one final step called Duplicate Address Detection, or DAD. Basically, it sends out a specific neighbor solicitation message out to the link, essentially shouting into the void, "Hey, is anyone else out there already using this specific address?" If another device actually is using it, it'll shoot back a neighbor advertisement. But if the PC hears crickets, nothing back, it knows for sure that its self-generated IPv6 address is completely unique and 100% safe to use on the network.
You see, the true elegance of IPv6 isn't just in that massive, mind-boggling amount of available addresses. It's really in how efficiently it handles things like SLAAC and duplicate detection to make large-scale networking virtually plug-and-play. As we transition completely away from the old constraints of IPv4, understanding these mechanics leaves us with one pretty crucial question. With all these tools and protocols now laid out before you, is your own network architecture truly ready for the massive scale and automated configuration of IPv6? Take these concepts, apply them directly to your CCNA studies, and keep exploring. Thanks so much for joining me on this explainer, and I'll see you next time.
Thank you for watching. See you in the next episode.